Assalamualaikum dan salam sejahtera. So we continue for part B for steady state heat conduction. So next we are going to look at conduction with heat generation and fin problem or fin analysis. So so we are going to look at conduction equation with heat generation mainly because of conversion of energy produces heat generation. So we are going to put E gen, or we call it heat generation, in our conduction equation. So E gen can come can come from exothermic process, okay, which is positive heat gen, okay, and it can also comes under exothermic, for example, combustion and conversion of electric energy to thermal energy. So, for example, let's say you have an engine, okay, three-cylinder engine. So each of these each of the circle is the piston that moves out and down. So if you measure the temperature over here at the surface of the engine block, the temperature will increase. Why increase? Because of this process, combustion process, produce a heat generation. Okay, positive heat generation that causes the temperature to increase. So in our analysis, we are going to look at one-dimensional analysis. Okay, steady state assumption, constant thermal conductivity, uniform heat generation, and this is an additional we are going to look at asymmetric surface condition. So in general, uh, if we were to write the basic 1D 1D conduction equation, so this is the equation, right, for Cartesian equation. So if you want to solve this, you integrate twice and then you can get a Tx equal to a formula. But in this case, we have heat generation. The heat generation exists, so we have this sort of equation. So E dot gen is a volumetric phenomena, meaning that the heat generation occurs over this volume. Okay, so the heat generation is a volumetric phenomena. So every point you will receive or you will feel the E dot gen. It's not a dimensional property, meaning that what that means is let's say E gen is not a function of x. No, okay, it's just a constant, and it fulfill everything in the volume. All right, so with heat generation, you have this equation, okay, and then if you want to solve this, obviously you need to do the integration, and then you will have this formula. Okay, so if we are working with 1D Cartesian coordinate equation, equation in Cartesian coordinate without heat generation, so this will not exist. So what we have normally is this one. But since we have heat generation, so we have additional parts over here. So the next step is to look at the boundary condition because we have integration constant. So for this case, for this wall, we are going to put a datum at the center of the wall. So this becomes 0. So to the right is positive, to the left is negative. And then you have positive L, which give you the thickness, the half of the thickness of the wall, and minus L, another half of thickness of the wall but to the left. So in this case, we have T surface 1 at negative L and T surface 2 at positive L for boundary condition. Remember that we have C1 and C2. This is a second order ODE, therefore we need two boundary condition. So this is two boundary condition, 2BC, that we need to plug in to here in order to get what is C1 and C2. So if you solve that equation, okay, and then you solve the equation, but you keep the constant to be Ts surface 1 and Ts surface 2, so you will arrive at this formula. Okay, so if you solve this, this is the form that you will get, which includes the heat generation. So it seems mathematically heavy, but it is not. It's just an you know just a basic quadratic equation. So E gen is normally is given in watt per meter cube. Watt per meter cube. Okay. So L is the half length of the wall. Okay. Because we start at the center. So K is the thermal conductivity of the wall or the material that you are investigating. So this S2 is the boundary condition S2. TS1 is here. Okay, and then the rest is a basic equation. So from here, second order ODE with heat generation, you do the maths, you do integration twice and plug in the boundary condition. This is the first BC. This is the second BC. And then you will arrive to this formula. Okay, so assuming that we have a value of heat generation, E gen, and then our left wall is 150 degrees C, and our right wall is 100 degrees C. And if you plug in all the values in here, this is the line that you will get. Okay, 150 on your left hand side, and 100 at your right hand side. Even though you have heat generation, but it doesn't really show significant changes because this is a linear equation. Okay, you have a straight line. So what happens if you switch? Meaning that instead of having 150, so 100 you send over here, on your left side, and 150 you send on the right hand side. So the gradient will just shift, mirror image. Okay, you have this is a negative gradient, you have a positive gradient. Okay, but in this case 100 on your left hand side, 150 on your right hand side. Alright, if you want to see the effect of heat generation, so we keep both wall to be the same. So 100 on left, 100 on the right. So 100 on left and 100 on the right. So with heat generation, you can see a parabolic profile. So the maximum temperature will be at the center of the wall or a datum. Okay, so I think I assume E gen to be 1 watt per meter cube, and then I plug it back in the equation. So this is what you will get if you have both wall to be at the same temperature, plus you have heat generation. Okay, it is similar to the first order ODE. Oh, not first order ODE. It's similar to heat conduction equation, which we learned earlier part of heat conduction, but right now we add heat generation. So that's why you have a curve, parabolic curve that looks like this. So okay, what happened if E gen we have both wall at 100 degrees C? What happened under steady state? What happened if we don't have E generation? Meaning that there is no heat generation, so you can basically cancel this out. Only with then you have only this equation. So if E gen equals 0, so your temperature profile across the wall will be 100. So just a straight line. So this makes sense because there is no temperature difference. So therefore your 100 degrees C will be straight line. And what happens if your E gen increases? Meaning then you start with 100 watt per meter cube, and then you have another one is 10,000 watt per meter cube. So your profile will look like this. You have parabolic profile. At the center will be the maximum temperature. This is max temp. This is also max T, but this is for the case of 100 watt per meter cube, and this is for 10,000 watt per meter cube. So if you have higher heat generation, your temperature profile will increase. And what happens if your heat generation is negative? Right? So if negative, your temperature will drop lower than its boundary condition temperature. So because this sign will be negative. But the question is, can Egen be negative? Okay, can heat generation can be negative? The answer is yes, but it's rarely to see that you can have a negative heat generation in a electrochemical process. So for example, a battery system. So you can have during discharging, you can have some at some state of charge, you can have negative heat generation. There are some process in electrochemical process. The process uh, will will absorb heat. Therefore, you have negative heat gen, but not that much. Normally, we have this kind of thing in mechanical perspective. Normally, we have increase of heat generation, and then we are looking at this sort of trend. Okay, since both of the wall are identical in terms of boundary condition, so this is the equation. Okay, we can manipulate this equation instead of having all from plus L to minus L. We can have only half of it. Okay, and you arrange your equation, and then you will have this form. So in this case, you know the T naught here is the maximum temperature. T as a T surface. If you want to know what is the temperature in between T naught and Ts, so you can use this equation. Alright, this is additional information. Um, so previously what we have here is fixed temperature. So what happen if we have a boundary condition which is not a fixed temperature? In this case, we have a boundary condition of convection. So heat from the wall is being expelled to ambient. So originally, this is our equation. Okay, um, this one. So if we have we have convection boundary condition. So we need to rearrange this and plug into this form of equation. A similar uh, setup to the 1D heat conduction equation. So apart from we have only the heat generation term inside of our equation. So rearrange your boundary condition and plug in back into the main equation. So this is a convection boundary condition. So heat from the wall is absorbed through to convection. And you can also have adiabatic surface, meaning that the heat cannot go out. So dq over sorry, not dq, dt over dx is equal to 0 at this region. So you can have convection and you can have adiabatic surface. Alright, so next we are going to look at the Finn's equation. So, or extended surface. So the Finn equation or extended surface stems from this equation, the convection equation. Okay, so in your motorcycle cylinder block, normally you have a fin, CPU, cooling system, you have fin. So basically that is for pulling heat away from the base by using extended surface, and this extended surface is governed by convection equation. So if you want to keep your system, let's say this is your system, your cylinder block, and then you have fin. So let's say to make a just example, so let's say we have 3 fin, 1, 2, and 3. So if we want to pull more heat from the system, we need to increase the surface area. So meaning that adding more fin. Okay, and then if we want to increase this Q, okay, what we can do is make A large. What else can we do? So we can make our ambient to be smaller. Okay, ambient to be smaller. So we can have larger delta T. But obviously it's difficult to control ambient. So you cannot control the weather. So we just keep it like that. So next what we can do is adjusting the H. Okay, adjusting the H is about the flow field. You can put a pump over here. You can put a fan to make sure the flow of air or liquid that passes this fin is higher than before. But that requires additional power like a fan or pump. So fin is a combined effect of conduction and convection. So for example, let's say you have a hotter region over here. This is hotter region. This is colder region. You want to pull heat away from the hotter region. So you put a fin. What happen is a fluid will flow across the fin and create a delta T. Remember that if you have delta T, you will have Q. So the heat will move that way. So in general, we have several fin, but the aim is similar, pulling heat away from the base. So uh, this is the base. Okay, this one is the base. This is the base. This round circle is the base, and this one is the base. So we can have a variation of um, area, okay, or design, I would say. But the main thing is to pulling heat away from the base. So different shape will give you different equation, but the base equation is the same because we are integrating over different surface area, and then we will having different equation. But the base equation is still the same, which is this one. Okay, so in general, we are applying energy balance equation in certain area of it to come out with the fin equation. So the rate of the heat conduction into this element X, okay, is equal to rate of heat conduction from the element X plus delta X and rate convection from the element. So from this equation, from this statement, and we end up having this equation. Okay, this is part of conduction equation and convection equation. So rearrange this, okay, to make it simpler. Instead of T, we change to delta, where delta is T minus T ambient. So T is that T at the fin. T ambient is your ambient temperature. Okay. From here, you can change to delta. And this parameter, this is the heat transfer coefficient. The unit is watt per meter squared degree C. This is the perimeter of the fin. K is the thermal conductivity of the fin. AC is the cross-section area of the fin. It's not the top and bottom area, which is exposed area. This is the cross-section area. So these four parameters is simplified in by this m squared. 1 m squared because it's purely mathematic. Is want to reduce the complexity of the equation. But don't worry much. We don't need to solve this. We are going to look at the table to to choose the equation that we need to use based on the geometry that we have. Alright, so this is the final version of the second order ODE. When we solve this, okay, and the solution for this is this equation. Okay, we have C1 exponential A. So A is your m, and your m is square root of HP KAC. This is m squared. So if your m is this one, okay. So from second order ODE, the aim is to always get the equation, the ODE, the formula. So this is the formula. So looking at this, we have C1, we have C2. Our goal is to find what is C1 and what is C2 from a table. So theta naught or theta 0. Theta 0 represent the base of the fin. Okay, where the base of the fin in theta is your T base, your temperature of the base, the fixed temperature of your base, minus your ambient temperature. For example, let's say your base temperature is 80 degrees C. Okay, and your ambient temperature surrounding the fin is 25 degrees C. So your theta 0 is 80 minus 25. Alright, as I mentioned earlier, so we want to find what is your C1 and what's your C2. What is your C1 and what's your C2. So we have four main boundary condition. Infinitely long fin, we have a negligible heat loss, specified temperature, and we have convection. So before going detail into this, let's look at the simple fin. Okay, this is fin. So this is the base. Okay, and this is the your fin. So what does it mean by infinitely long fin? So we assume, let's say we have a fin that has a length of 5 centimeter, not that long. But to make our problem at some point easier, we assume infinitely long fin. So this will turn your fin to very long fin. Okay, infinity. So this is what it means by infinitely long fin. So there are certain cases that although your fin is 5 cm or whatever length, we assume it to be very long, so that your tip temperature can be equal to your ambient temperature. So your tip temperature over here will equal to your ambient temperature. If you make it short, okay, let's say your base temperature is 80 degrees C, your ambient is 25 degrees C. So you cannot have your tip temperature similar temperature with the ambient because your fin is short. So if you make it very long, you can have your tip temperature is equal to your ambient temperature. So that is for infinitely long fin. So let me delete this first. Alright, so next we are going to look at negligible heat loss. For negligible heat loss, we assume that the tip of the fin is insulated. Therefore, the heat transfer in this direction, the heat transfer can occur, but not crossing the boundary. Okay, it cannot pass because we are assuming that the tip is negligible heat loss or adiabatic. Okay, so the third one is specified temperature. Specified temperature means that we fix the tip at certain temperature, meaning that let's say your base is 80 degrees C. So we mentioned that okay, the tip temperature is 40 degrees C. It's maintained at a fixed temperature of 40 degrees C. So the last one is convection. So for convection is you have a tip, the Q will go to the ambient. So if I write the mathematical boundary condition, K dt dx is equal H T minus T ambient. So we are losing, we are giving heat to the ambient. That's what it means by convection. So I hope that clear in terms of physical representation of these four boundary condition. Okay, although they are different in terms of boundary condition, they are sharing the same thing. Okay, we assume the Q travels only in this direction. Okay, the Q travel only this direction. The Q does not travel, does not go there, does not go there. It's like even though we have a fin, but assuming the top and bottom of the fin is insulated. So if you want to consider top and bottom, we need to do 2D analysis, which is very quite lengthy. So in order to do 1D, so we assume it to be top and bottom to be insulated, and then we are only changing this boundary condition at the tip. So we have infinite long fin, negligible heat loss, specified temperature, and convection. So we are going to look at infinitely long fin. So remember that from the general ODE, second order ODE, where we solve and then this is the equation that we get. Remember that I only mentioned that we want to find what is your C1 and what is your C2. So in this in case infinitely long fin, our boundary condition, okay, the first boundary condition is theta B. Theta B is your base temperature. So this is your fin, this is your base temperature minus the ambient temperature. And your boundary condition at the fin tip, meaning that the farthest away, okay, your end of the tip is 0. Okay, so why 0? Because if we make the fin to be very long, as I mentioned earlier, so your tip temperature will be equal to ambient temperature. So T ambient, basically your TL is equal to T ambient minus T ambient, and then you get 0. So in this case, if you assume like that, you can use this equation directly. Okay, So this equation will help you to find what is the temperature at certain point, okay, on the fin. What is the temperature for the certain point of the your fin? For example, your fin is let's say 10 cm. Okay, you assume at the end tip of the fin to be similar temperature, so 25 degree C, and your ambient is also 25 degree C. So that allows you to use this equation. So you don't have to look at this and this one. Straight away use this equation to determine what is your temperature at along this fin. So that is for temperature. So if you want to calculate how much the heat transfer rate, meaning that how much heat is travel that way, what is the value of Q that travels from the base to the end of the fin. So this is the basic Fourier equation. So because this is the case of infinitely long fin, so you straight away using this equation, and you can get the answer in watt. So next we are going to look at negligible heat loss. So this is your fin. So this is insulated. Okay, the first boundary condition is this one. Your base is TB. Okay, and because this is insulated, so d theta over dx is equal to 0. But we don't have to put this into here. Okay, you don't have to. You can use this equation directly to calculate what is the temperature along the point. And the corresponding heat transfer rate, this is the general equation. You can straight away using this equation. For specified temperature, so we have a fin. Let's say this is 25, your base, and then your tip is 10 degrees C. Okay. So your ambient is maybe 8 degrees C. Okay, very cold. So you need to find what is your theta first. You cannot use directly temperature because the theta is your solution. So in that case, uh, your theta will be 25 minus 8. In this case, 10 minus 8. Okay. But for your equation, so if you want to calculate or find the temperature this way, you can use this equation. Your m is equal to okay, remember that we have m over here. Okay, equal to this one. Okay, and this you will need to use the exact temperature in degree C. So what is your TB? What is your TL? TL is your temperature farthest away from there. So your TX will be your temperature that you want. Okay, remember that L is the maximum length. Let's say this is 10 cm. Let's say you want to find your temperature at 5 cm. So this is 0. This is 10 cm. You want to add 5. So simply replace this with 5. Okay, and this data with 5, and then you can get your Tx or temperature at 5 cm. So if you want to calculate what is the heat transfer rate for this sort of boundary condition, okay, you need to use this equation. Yes, it seems mathematically very lengthy, but we are going to use the equation straight away. We don't need to use the we don't need to derive. Okay, but of course the derivation are there, but not covered in the chapter. So next we are going to look at convection. So assuming that this is the fin, this is base, okay, and heat gets out from the end of the fin. So this is the equation. T minus T ambient. Oh. Right. So this is the first bonding condition. This is the second bonding condition. So couple these two things. Okay, put in this general solution. This is the temperature profile or temperature equation if you want to find a certain temperature along the fin. Okay, and for heat transfer rate, you use this equation. Alright. So we have looked into for corrected fin length. So we have looked into convection. So basically, if you look at this convection equation for conduction and conduction for temperature and heat transfer is very lengthy. But we can use corrected fin length, okay, by assuming instead of convection, we assume it to be insulated, okay, but we need to add certain length over here, okay. What I mean is, if you have a problem, this is your actual problem, where your end of your tip is convection boundary condition. So if you want to use the convection boundary condition, this is the equation that you are going to use. This is very lengthy. So if you don't want to use that, you can use insulated case. Okay, in this case, this is a negligible heat loss or insulated. The equation is straightforward, but okay, equation number 1 and equation number 2. This is for temperature, 2 is for heat transfer rate. But but it is very straightforward as compared to convection. But you need to add certain length. Okay, what we call a corrected fin length. So you need to calculate uh, the cross section area, divide by its perimeter, and add the actual length. So what happen is over here is you basically extend this a bit, and then you can cancel convection and replace with insulation. Okay. So in general, this is the equation. But if you simplify it, so basically for rectangular fin, your corrected length is your length plus the thickness divided by 2. This thickness divided by 2 is your corrected length. For cylindrical fin, basically your fin is round diameter. Okay, so your corrected fin is L plus D divided by 4. Okay, so if you want to use the long equation for convection, no problem, go ahead. It's not the wrong way. But if you don't want to deal with this, you want to change your convection to insulated, but remember you need to add this part, and you can use the equation for insulated. So this is equation for insulated. Okay, this is the temperature profile, this is the heat transfer rate. So next we're going to look at fin efficiency. Okay, so ideally, this is ideal condition where we want to pull heat away. So as for example, let's say your ambient is 25 degrees C. So if every fin from the base to the end of the fin is 80 degrees C, that will be very ideal. Okay, but eventually the temperature will deviates from 80 because the heat transfer rate is not similar at each location. Therefore, you have a temperature gradient. So this is actual. So assuming that you have an ambient temperature of 25 degrees C, so you will have a different temperature along the fin. So 80, 70, and 56. So if you want to calculate what is the efficiency of the fin, so actual heat transfer rate from the fin, if this one, and sorry, the actual is this one, and the ideal heat transfer rate from the fin. Okay, if the entire fin were at the base temperature. So this is ideal, the actual divided by ideal, and then you can get your fin efficiency. So your ideal heat transfer rate, is basically your maximum it can give. Okay, maximum it can give, because everything over here is similar temperature. So you can use the T base lab 80 minus 25 given the heat transfer rate, and A fin is the surface area of the fin. Okay, if you want to calculate this one, this is 2 pi r L. So this is the radius r, and this is the length. Okay, so this is the area of the fin, basically the maximum. But we also can apply a different bonding condition to calculate the fin efficiency. For example, let's say you have in case of infinitely long fin, you assume the fin is very long, so that you can assume that the tip temperature is equal to the ambient. Of course, your base temperature will be different. It's not equal to ambient. So in that case, if you want to calculate the fin efficiency, you can use this equation. Okay, this is the derivation, and then you have ended. You end with 1/ml. So if you are applying different bonding condition, okay. So your efficiency for case of adiabatic, this is the equation. But remember that we have the similar for the ideal. HA TB minus T ambient. This is also, but the difference is only at the actual. So actual for this is for this case, and this is for adiabatic tip. Alright, so everything is tabulated. Okay, you can find all the data in your heat transfer book. Okay. So what is the corrected length, what is the M, what is the efficiency, so you can use the table in your book to basically calculate the parameter or the value that you want. So the design consideration for fin length, so the longer the fin, the larger the heat transfer area. In technically, yes, therefore higher heat transfer rate from the fin, but it comes with a price. So if you make the fin very large, you will increase the mass, and then increase the fluid friction. So therefore, we want to calculate what is the best. That's why we calculate efficiency to basically determine is it okay, acceptable or not. So next we are going to look at the extension for efficiency, or we call it fin effectiveness. So there is no assurance that adding fin will enhance heat transfer. Okay. So the fin effectiveness will serve as a judgment. So based on the enhancement in heat transfer relative to no fin case. So in this fin effectiveness is basically want to calculate whether adding fin will help in terms of removing the heat away. Okay, but the goal of the fin, of course, you want to pull out Q from the base. But from the fin effectiveness calculation, then we know whether it's effective or not. Okay, so this equation in terms of fin effectiveness is the Q fin is the heat transfer rate from the fin base area, okay, divided by heat transfer rate from the surface of area AB. Okay, so Q fin is the heat transfer focused solely on the surface area of the fin. Okay, divided by the heat transfer if you don't have fin at all. So this is you don't have fin at all. Primarily depend on this area and the flow around across that on the surface of the AB, depend on the heat transfer coefficient. Okay, so this is equation reflect this one. So Q fin reflect that one. The we rewrite as Q fin because this depend on the boundary condition, depend on the type um, of the geometry of your fin. Okay, so Q fin can be anything. It depends on your boundary condition and type of your fin. But Q no fin, this is the equation. So if you find the ratio equal to 1, meaning that the heat transfer with fin is equal to heat transfer with no fin. So in that case, why bother to put fin? So just leave it like that because you have heat effectiveness of 1. So if you have effectiveness less than 1, maybe 0.1, 0.05, so that indicates that the fin acts like a insulation, or the fin slows down the heat transfer. So what happens if you have this? You will accumulate heat on the base. So your base will be hotter than ever. So this is what we want. So effectiveness larger than 1. So indicates that fin enhance heat transfer. Okay, so this is what we want. So meaning that the ratio or the Q fin is larger. The value of this one is larger than Q base. So meaning that it's effective in removing heat. Okay, for this equation, is you can use if you have the fin efficiency, okay, multiply by the base, okay, and you can get the actual Q fin, and Q fin divided by the base with no fin, you can get the effectiveness. So this is the interrelation of efficiency and effectiveness. So for the case of if you have a very long fin with uniform cross section, so you need to find what is the heat transfer rate. So this is the heat transfer rate for the case of very long fin. So you go back to this one. So this is the heat transfer rate for the case of infinitely long fin. So you take that equation and put it there, and what is the heat transfer rate with no fin? So this is general equation of it. So you end up having this one. So from here you can calculate what is your effectiveness of the fin. Alright, so in general, even when designing a fin, okay, we need to focus on the material that has high thermal conductivity. So the ratio of perimeter to area must be high as possible. The perimeter must be high, okay, because we want to have a larger surface area. And the use of fin is effective in low convection environment. So we don't want to add extra pump or extra work basically to force the air to flow around the fin. Okay, we just want to use the fin, focus on the fin to improve heat transfer rate or increase the heat transfer rate. So you can have a look at the textbook for overall effectiveness. Okay, so this is what I mean by it's not increasing the fin will increase the heat transfer rate. So if you make your fin very long, okay, with the aim to increase the area, surface area, okay, you can look over here, the temperature gradient will start to deviates at this point. Okay, this point and above, the temperature will be similar to your ambient temperature. So why you need to install very long? So up to this is perfectly fine. This is where high heat transfer rate occur. Okay, the Q is generally higher at this region. Why? Because the delta T is higher, and then the Q slightly drops when you move to the right, because the delta T is getting smaller to the right. At this point, there is no Q, because the ambient temperature is similar to the fin temperature at this stage. Okay, so AL is the parameter of the fin. Okay, so they are looking at the effectiveness by using this equation. Alright, let's look at one example. So we have this fin, okay, and then using table and figure, we want to calculate the efficiency, heat transfer rate, effectiveness of the straight rectangular fin. Okay, the T base, the temperature of the base is 350. Okay, this is T base. Thermal conductivity is 235. The air temperature is ambient temperature 25 with heat transfer coefficient of 154. The length is 50 millimeter, width is 100 millimeter, and the thickness is 5. So from the table 3.3, so in this case of straight fin, we assume it to be infinitely a long fin. Okay, so you can use this equation. Okay, this is m. The constant of m consists of the heat transfer coefficient, the thermal conductivity, and the thickness. Okay, next we want to find the corrected length, okay, and the area of the fin. So next you can use this equation in the table to get the fin efficiency. So basically 81%. And then we want to calculate heat transfer rate. So for heat transfer rate, because you have efficiency right now, you can use the base equation, the heat transfer without fin, multiplied by the base, you can get the actual. Okay, in this case 427. So this equation is heat from base. This is without fin. But if you have the efficiency multiplied by this one, you can get the actual. Okay, and then you can calculate, the next thing you want to calculate the effectiveness. So this is the equation for effectiveness. So AB is the base of the fin without the fin. Okay, so basically this is your, the dotted line is your AB. Okay, it's your AB. Q fin is your actual divided by your base. You can get your effectiveness of 17.1. So this indicates that fin helps, because the value is E is larger than 1. This adding the fin will help the heat transfer. So we look back at this one. So more than 1, the fin enhance heat transfer. So it's a good thing, the good design, because you have effectiveness of larger than 1. So that's all for the chapter of conduction. Thank you.